final bit of the puzzle is given by allowing us to use type parameters in the definition of algebraic data types. In fact, we've seen one already, the example of lists. We have the list type constructor has one argument, which is the type of list it is producing, and the constructors are empty and cons. Cons take something of type A and something of type list of A to give us something of type list of A. So A stands for an arbitrary type. We can build lists of any type, just like a variable stands for an arbitrary value ordinarily. So that's how lists are or can be built under the hood, as it were. Here's an example, which is, it seems like a very simple type is called maybe A. And there are two kinds of things in there. There is nothing, single value nothing, and then there's just applied to A. So it's like adding one more element to the type A to say, oh, there isn't an A, whereas just A is something of just one element from A. And how might we use that? Do you remember in the last segment we talked about defining the root of a tree? And we had the case when the tree was empty that there wasn't a root, and we called an error. What we can do now is define a safe version of that function, and instead of it returning an integer, it returns something of this maybe int type. So in the case of applying safe root to empty, we get the answer nothing. Whereas if we apply safe root to node with the value n as the integer, we return the result just n. So now if you were the caller of this function, you don't get a number back. You get something of type maybe int, and that means you are responsible for dealing with the case that the tree doesn't have a root. And that's fair enough. You called the function, so you'd better deal with that case. And the definition here is forcing you to do that because it's not giving you an int, it's giving you a maybe int. And so you will have to check whether that thing is nothing. If it's nothing, you need to do one thing. If it's just n, then you can extract the n and work with it as a number. The next example shows you this handling of results of maybe types in practice. Let's look at this. What I'm defining here is a safe maximum function. It takes a list of integers and returns a maybe integer. Why are we wanting a safe version? Because we don't know what the maximum of the empty list is. So we say, well, safe maximum is nothing. And then what do we do in the case of a list x cons x's? So the first element is x, the remainder is x's. Now, the maximum may be x, or it may come from getting the maximum of x's. But remember, when we apply safe max to x's, it will return something of type maybe int. So we know its answer is going to look like nothing or just y. And so what we write here is a case expression that pattern matches on the result of safe max. When you write case expression of, it evaluates the expression and does a pattern match on the result. So this calls safe max and says, if the answer is nothing, that is, x is the empty list, then the maximum of the whole thing must be just x. On the other hand, suppose there is a maximum of that, a properly defined maximum of x's, that would give us the result just y. And now we've got two candidates for being the maximum of the list. It's either x or it's y. So let's take the maximum of the two, max xy, but we have to wrap that up in a just, hence the answer here. So the answer in the case that x is empty is just x. The answer in the case that x does have a maximum, which is y, is just max xy. But emphatically, the answer to this function is a maybe int. It's not an int. And as you see, when I called safe max here, I had to deal with the fact it might be nothing. It might be just x. Okay, good. A final example, we could make our binary trees parametric as well. And it's a trivial change that we have a parameter a to the definition, and instead now of storing a value of type int at the node, we store a value of type a. And that gives us, that's turned that definition from being a definition just over integers to being a definition over any type we like. And the definitions of functions over there will follow the same, exactly the same pattern as the definitions we've seen already for the monomorphic, the non-polymorphic definition of tree over integer.